you what the formal equation that we get for AK. The formal equation for AK is as follows. It's IDT AK. There's a constant which will play the role of our time scale later on. It's an accumulation of all the dependencies of L and epsilon that you do in the computation. But the main point is this integral. So it's the integral from -1 to 1, the integral over R2, AK plus lambda T, A bar at K plus lambda T plus Z curve, A at K plus Z curve dt long. We give the geometric significance of this integral on the next slide. But for now, let's three-parameterized time and define the slow time variable tau as follows. T is equal to T star tau. Then formally, at the equation specified by AK in the slow time variable is exactly this. We call this equation the CR, the continuous recurrence equation, or the CR equation. It's given by IDTG is equal to T of TDG, where T of TDG is given by this integral. So let me give the geometric the meaning of this integral. So C is fixed by the right-hand side. This is C plus lambda C. This is C plus Z plus, and this is C plus lambda Z plus. So what we're doing is that we're taking the function C. C is fixed by the left-hand side of the equation. We are evaluating over those three vertices of the rectangle, and then we are integrating over all rectangles having C as a vertex, and with the weight that is given by the system, so the particular weight that is given by the system. Because, in the rectangle you have to decide which side is smaller, shorter than the other. It's the symmetry. Yeah. Okay, so this equation turned out to be new, even in the physics literature, and it can be considered as a deterministic analog of the wave kinetic equation. And the main difference between this equation and the Kolmogorov vector of wave kinetic, which is that this equation is Hamiltonian. We have preserved the Hamiltonian factor in the process, and the Hamiltonian is given by this a priori complicated formula. But the first surprise is that this formula is not complicated at all, and the Hamiltonian of this equation is nothing but the algorithmic reverse form of R1. This means that if you want the Hamiltonian of G, all you have to do is apply the linear Schrödinger propagator on R2, raised to the power 4, and integration straight on time. Okay, so before I talk about making all this rigorous, I would like to talk about some properties of this equation. Okay, so first in terms of conserved quantity, yes, so you can change variables, and this you can write it as 1 over 4 the integral over all the parts. So this is a lot of symmetry in this integral. And then this is a four-line computation. Okay, so the following property quantities are conserved by the law of CR. Of course, the Hamiltonian itself is conserved. The mass is conserved, the momentum is conserved, the position operator, the second moment of the position is also conserved, the kinetic energy is also conserved by itself, and so it's angular time. So probably the most surprising conserved quantity that this equation specifies is the invariance under the Fourier transform. This means that if G of T is a solution of CR, then its Fourier transform is also a solution of G hat T is also a solution of CR. Moreover, we have that the Hamiltonian function itself is something, it is an invariant under the Fourier transform. But if you know that the Hamiltonian, once we realize at the end that the Hamiltonian is algorithmic personal, the fact that the Hamiltonian is an invariant function was very marked from previous. Okay. Another surprising image of this equation is that it is invariant eigenspaces of the quantum harmonic oscillator. As we know, so let us recall the quantum harmonic oscillator is the operator minus delta plus x squared, which admits an autonomous basis eigenvector for L2 R2. The eigenspaces EK and eigenvalues K, they are k-dimensional, and they are planned by the k-order function. This will be important when we study analysis of harmonic graphing, and so it's analysis. So the theorem states is that if you start in one of those eigenspaces EK, you will stay in EK for all time. So G naught is an EK, then G of T is an EK for T, but I should take to remark that this does not mean that the dynamics decoupled is finite dimensional for these, because if you excite a mode in one eigenspace EK and a mode in another eigenspace EK2, then this will excite everything dimension. You get an instance for these. Okay, in terms of global well-posedness, the equation has very nice global well-posed properties. It is globally well-posed in L2, so for any initial data T naught in L2, there exists a unique global solution which is continuous in L2 as well. It's also globally well-posed in XS for any S bigger than or equal to 0, and by the invariance of the Fourier transform, it's globally well-posed in the weighted spaces S0 as well. And well-posedness result that will be important when we do things rigorously is the well-posedness of the state X sigma, which is the state of functions that decay like X to the minus sigma at X goes to infinity, and this is true for any sigma bigger than 0. The final slide I have on the properties of this equation are on the stationary solutions. Actually, we have a lot of stationary solutions, but I'll mention only two. You might have guessed that the Gaussians will play an important role, so indeed for any alpha x of a function, we can calculate C depending on alpha such that T to the ICT times T to the minus alpha is squared close to CR. So these can be considered polytons even with the default CK. And these are coherent structures applying the symmetry group of the equation you obtain a 7-dimensional manifold of them, for which you have also stability because essentially they are ground states of the harmonic oscillator. The other important family of special solutions is important because it links the theory of this equation with the Kolmogorov vector equation or the wave kinetic equation. So we have the G of T which is e to the ICT over absolute value of C plus CR. And this, if you remember the Rayleigh-Jeans solution of the wave kinetic equation, this corresponds exactly to n of C plus C to the minus 2. Remember, n is the square of the frequency, and if you square this, this is exactly the scaling of frequency. And indeed, we have many other stationary solutions at each energy level of the quantum harmonic oscillator, and we can also write some quasi periodic solutions. Okay, so these are the only properties that I will talk about concerning this equation. Maybe here, when he comes here, we'll talk about more. But I would like to spend a few slides talking about how to make things rigorous and what this equation tell us about the dynamics of analysis. So ultimately, what we'd like to do is we would like to project the dynamics of this CR equation, and we have seen that they are quite rich, and we'd like to analyze on a box of size L where L is finite, or even on the T when L is equal to 1. So for this, suppose we have an interesting solution T of T over of the CI equation on an interval of size interval 0 m. And here it is absolutely crucial that we can take m arbitrarily large, so that we can project any long-term dynamics we discover on the CI equation into that of NLS. And so suppose we have such a solution, what we'd like to do is we'd like to construct a system of NLS that carries the dynamics of 0. And to do this, we do the natural thing. We start with solution for NLS that initially at time 0 is given by the same initial data for the CI equation. So AK at 0 is equal to G naught at K. And at later time, we would like to approximate K at time T, but G actually first describes time T over G, but actually you realize that you need to compare it at time T over T star because at some point in the formal derivation I still find we had that formally minus IDK was 1 over T star T over K. Okay, so and in order to do that, there are three main difficulties one needs to overcome. The first difficulty is justifying the passage to the resonance system. That was the very first approximation that we have done. And this is usually done by a normal form transformation, but this is not as simple as one needs to make things very be careful about making things very quantitative. Well, yes, so in the limit L goes to infinity, the resonance almost doesn't, well, not everything, but there is not, I mean, if you can have K1 omega bigger than any number, can be bigger than 100. But it can be as small as 1 over S squared if it's not 0. Yeah. Okay, so this normal form transformation is essentially a change of variable transformation that allows you to write the equation as the contribution of resonance interactions plus the contribution of non-resonance interactions so that you can treat them as perturbation. And if you do that, it allows you indeed to write this equation for AK as the sum of the resonance interaction plus the contribution of non-resonance interaction, which you can truly estimate by order of Epsilon for as the 0 plus. And the 0 plus means as the delta for any delta positive. Okay, we'll revisit this problem, this equation in a few seconds. The second difficulty is obtaining good discrete to continuous error estimates, which means essentially making rigorous the passage from sums to integrals that we have done, and this requires some tools from analytic number theory, mainly the Modis inversion form, essentially the Modis inversion form. But the most challenging difficulty, which is not a priori obvious, was obtaining sharp estimates on resonance sums. And this was challenging because it was related to offline sharp periodic regard estimates. So let me explain why this difficulty shows up. Yes. The time scale T star over here. It's epsilon to the minus 2 L squared over epsilon to the minus 2. Yes, there is one. Okay, okay, so let me explain why this is something that is very important. If we look at this equation, our whole premise would, remember when we derive the CR equation, we throw away those interactions. So our whole premise is that the resonance interactions dominate the dynamics. They dominate the contribution of non-resonance interactions. In order to prove that, you need a very good estimate on resonance interactions. So we need to estimate this sum. So from this slide is a completely harmonic analysis slide. So what we would like is that we would like to take three sequences, AK, DK, and CK. We would like to form the resonance sum out of those sequences, and we would like to estimate this in a Sambana straight line, which we have some liberty in choosing, for a constant that depends on L times AK in X, DK in X, and CK in X. Now, the formal argument that allows us to derive the CR equation tells us an idea what this constant should be. Of course, we are very interested in the determinant of this constant now. The formal argument tells us that this constant cannot be any better than L squared log L, because L squared log L is actually achieved if the sequences AK, DK, and CK are actually smooth sequences. They are achieved. The second observation that maybe one can do is that if we decide to work in Sobolev spaces, to work in L2-weighted spaces, so the spaces correspond to L2-weighted spaces for your space, then this estimate becomes equivalent, completely equivalent, to the following still-open-sticker estimate on T. And this estimate reads as follows. You take phi in L2 of T2, you project it onto frequencies less than or equal to n, so this is T less than or equal to n, and then you apply the linear Schrodinger propagator. You estimate this in L4 space-time, and what you really want to estimate it by is logarithm of n to the power 1 over 4 times L2 naught. And this estimate was implicit in the work of Bourgain in 93 and 96, but it's still open. And sigma, where is sigma? Any sigma, even sigma equal 100, you have to answer this. Because at low frequency, when k is less than 1, this is equivalent. The way you can raise it, or for any sigma, equivalent. For sigma 0, yes, as well. Yeah. But even if you take I want to emphasize that if you take sigma equal 100, it does not solve this, because when k is less than 1, you find this. You remember k is in Z2 over S. Okay, so this estimate turned out to be quite a strategy for us to prove. So if you are really bent on working on an L2-based space, there's no other way than answering this question. But we have the liberty of choosing this norm X, and if you work in an L-infinity-based space, so if you work on sequences that decay like k to the minus sigma, and X goes to X, k goes to infinity, then this estimate becomes slightly more tractable. It's still quite a substantial part of the work, but we can prove it with the sharp constant G of L, which is L squared log L. And here I should also point out that it is absolutely crucial that we get the sharp constant. Any loss of any power of log L would select. Because either you get the most strong statement you are shooting for, and you are unlucky, or you don't get anything. So here you really need the sharp constant L squared log L. Well, it came from, as I said, it came from one way to see it is if you think of AK, DK, and CK as being traces of smooth functions, then if you change the sum into an integral as we did in the derivation of the CR equation, you get the log L. Alright, so that's the point number 6 numerological, I would say. Yeah. Actually, the lower bound that this should be bigger than log N was now that we have this, the corollary that I would like to say is that proving this estimate in the space X sigma gives you a periodic figure estimate at the Planck scale, which until now we don't have any such estimate. But of course, with this C2 replaced C in A2 replaced by C by a norm that is an interpolation of N1 and N3, but the key point is that this norm behaves exactly like that. And this is the crucial part. You want a critical norm that behaves exactly like that with the sub. It's a scale. It is a scale. If you have a solid, then it's very bad. Yeah, it gives you too many factors, it gives you less support. Yes, so we knew this, that this is, everyone knew that this is just an anti-epsilon from Bourg-Sampson, right? For any epsilon. But anti-epsilon would give you as the 2 plus epsilon over here, which is, you really need to take that one. Okay, maybe I'll if I have time, I'll go a little bit for you really figure out what I lost there. Okay, so let us go back to our problem. Now that we have a very good way to bound resonance sum, we can go back to our problem, which is estimated resonance sum in comparison to this. So this is our NLS equation. The sharp estimate on resonance sum as above tells us that the resonance interactions are essentially order of epsilon squared locale over epsilon. So this is a caricature of the proof. And for those resonance sums to dominate the contribution of non-resonance interactions, all you need is that epsilon squared log L over L squared is bigger than epsilon to the 4L, which is the found of non-resonance interaction. And this gives you the restriction epsilon less than L to the minus 1 minus. And this is called in the physics research space regime. It is exactly the regime where the resonance system dictates the non-linear dynamics. And we'll talk a little bit more about this restriction, especially in terms of comparing it with the restriction that you have in this theory. But for now, let me explain why you really need to sub on the figure test. So if you, what you'd like to do, you'd like to compare AK of T with G times G over T star. Okay, so we take initial data AK at time 0 T equals to G at time 0 at K, the base of K, and then you define the error, which is the difference between AK at time T minus G at time T over T star. And again, recall that formally we had that the right-hand side of NLS converges to 1 over T star times the right-hand side of the CR equation. So we should compare AK with G at time T over T star. And to do this, the equation satisfied by EK is the following. This is the right-hand side of the NLS equation, and this is the right-hand side of the CR equation. What I will do is that I will add and subtract the resonance sum having its candidates from the solution of the CR equation. Okay, the estimate on this sum is this second difficulty that I talked about, which is making rigorous assemblies from discrete sums to the continuous integral. But it is the first line that I would like to focus on here. And this is the line that will tell us why we need the sharp estimate. Okay, so this is the equation for dt of AK. I have dt of AK, dt of EK. From this, I have equals to epsilon squared L to the minus 4. The sum over RK, because I'm subtracting a granular term in AK from G, I will have at least one factor of EK. So I have EK1, say, G at K1, or G bar at K2, sorry, G at K3 plus similar term. Okay, so if I take this in unknown x, dt of EK, okay, unknown x, and I will use the estimate of the resonance sum that we have, because this is less than or equal to epsilon squared L to the minus 4. The estimate of the resonance sum tells us this equals any resonance sum plus the factor of L squared log L times EK9. And EK9 is order of 1. Plus. Okay, so what is this? This is equal to epsilon squared log L over L squared, which is exactly 1 over T star. So what we have is that dt of EK is less than 1 over T star EK. Suppose I lost the factor of log L in the resonance sum estimate. And we take a constant over here that is strictly larger than 1 over T star. And as a result, I will get an approximation theorem over an interval that is strictly less than 1 over T star. But T star was the time scale of this function G of T over T star. So for time scale strictly less than T star, this function does not move, get a point straight. So in that sense is that either you get the sharp estimate over here, or you lose something and you don't get anything. Okay, so this is what I wanted to explain. Okay, so this is the proposition that allows us to go from the resonance sum to the integral, and if we write on some number 3 that I want to go into, but finally we can take our approximation result. So we take sigma bigger than 2, and suppose G of T is the solution of the CR equation on an interval 0 m. Again, I'm can be taken to the arbitrary bars. This is something that is very important to have delivered to using m. And the only condition we have is on the data such as G0 and x greater than or x sigma plus 1. Remember, x sigma plus 1 are the functions that decay like x minus sigma equals to 3. Again, sigma is globally reported for such initial data. Then if we take n large enough, and we take epsilon less than L to the minus 1 minus, which was what we call the restriction we had on the few slides ago, that is equal to 3. We take AK of T to be the solution of NLS, such that at time 0, AK of 0 is given by T0 at K. Then at later time, we can approximate AK at time T by the function G at time T over T star at K in the space X sigma by the constant over log L, so it improves to 0 and goes to infinity. And the key point is that the time interval of this approximation allows us to project both the dynamics of T on the interval 0 and NLS. And the reason for that is that if you evaluate this, if you apply this inequality at the endpoint of this time interval, which is m capital T star, you are evaluating G as capital M, which means that you have projected both the dynamics of G on the interval 0 m into that NLS on a constant like that for L large enough. But you can also, we have also an approximation theorem of T2, which comes just by scaling. On T2, we have to understand the CR equation as an equation for the frequency envelope of the solution. This means that we are looking at, okay, I lost my shock. Okay, so this means that we are considering solutions for NLS that are initially given by, or at any time are given by T hat at K, which is the frequency, the Fourier transform of the solution, is given by essentially a function of K over N. Thanks from normalizing function. So if this happens, we say that this is the example of T. Okay, so what we have is that you take G, that is such that G naught and its gradient are xs plus 3. Again, the global reward force plus data. The frequency scale is large enough. And we take G of T to be the solution of NLS, whose initial data is given by a normalizing factor times G naught at K over N. So at 0, the frequency envelope of G hat is given by G naught. This normalizing factor is chosen exactly to make G hat size 1 in excess, uniformly enough. Then at later times, you can approximate the solution NLS solution T with the solution whose frequency envelope is given by the solution of the CR equation at times T over T naught. T naught is the time scale in this case. And by a constant over log n, so it goes to 0 as n goes to infinity. And the key point again is that the time interval of approximation is long enough to observe any interesting dynamics of G. So if you evaluate G at time, if you evaluate this inequality at time T naught n, then you are evaluating G at capital N, which means that you have projected all the linear dynamics of G on the interval 0 n into that of NLS. And using this, using this theorem, one gets many interesting examples of coherent dynamics of NLS using the special solutions we have for the CR equation. And then this gets me to the following remark, which I would like to say. So we started motivating the Rashbox limit by saying that if epsilon was less than, we started by motivating the Rashbox approximation by saying that if L is bigger than epsilon to the minus 2, then NLS on R2 is your Rashbox, is the right equation to look at. And the theorem 2 slides ago, it tells you that if epsilon is less than L to the minus 1 minus, then the CR equation is the equation to look at. Okay, so this means that epsilon is less than L to the minus 1 half. So this means that the regime L to the minus 1 minus epsilon less than L to the minus 1 minus, less than epsilon less than L to the minus 1 half, where epsilon would go from. And it would be very interesting. It's very interesting to know what is the right effective equation of entropy. Okay, so this is very much, and you can do this for other equations. For example, up to now we have done it for, we already finished doing it for the one equality NLS, this correlation with the eta, and all the structure and symmetry is presented in this case. Okay, so in the remaining 5 minutes, I'd like to talk about one extra property of this equation, which makes it quite relevant in studying NLS with harmonic numbers. So as we said, we are interested in confinements that are either geometric confinements from above, or confinements by a potential, and this is the most well-known instance of a confinement by potential. It's a very important model in Bose-Einstein quantum state. When you study NLS, we replace the delta by minus delta plus x squared. This is a harmonic trapping. And if you want to understand the long-term behavior, we'll do as Nikolai did, and as we have always done, we conjugate. By IGST, the projection of the theta in space, and then you have the sum over T1, T2, T3 in N. T to the I lambda T1 minus lambda T2 plus lambda T3 minus lambda T3 plus T1 and T2 bar T. This is exactly this equation in Fourier. As we said, as you already have experienced, resonance interactions play a particularly important role in this case. So let us isolate the resonance system. The resonance system corresponds exactly to the system for which lambda T1 minus lambda T2 plus lambda T3 minus lambda T is equal to 0, and is given by the following system. IDTF is equal to RSSF, where RSSF is given by exactly the previous sum except that we restricted on lambda T1 minus lambda T2 plus lambda T3 is equal to lambda. In order to observe the Hamiltonian structure of this equation, we will rewrite R as follows. So I will replace this sum of lambda T1 minus lambda T2 plus lambda T3 is equal to lambda T over the sum over all T1 with F1, etc. And rewrite this integral as an integral from minus pi over 4 to pi over 4, e to the minus I tau h, e to the I tau h f, f bar, e to the I tau h f, eta. And this, I can observe it as GQ by GF bar, so it's where Q is the Hamiltonian of this equation, and the Hamiltonian is given by the following L4 secret norm, except that you have an H over here. Not that. So we're starting to see some similarities with the CR equation. In order to see the full similarity, we use the Lens transform. The Lens transform equation with harmonic transform. And especially that this is the relation. Q is the e to the RT delta phi, and G is e to the RT h phi, the U and G are related by this equation. But if you plug this formula into the previous formula for Q, you notice that all everything magically cancels, and you get the L4 secret norm with H, the same as the L4 secret norm with delta, and this is exactly the Hamiltonian of the CR equation.